Welcome everyone to a new episode of Embedded in a Nutshell. Today we will focus on the basics of the I2C protocol. After this short tutorial, you will be able to tell if I2C is the protocol of choice for your specific problem, understand the actual transmission flow, read and write registers over I2C, and debug faulty I2C communication. First of all, we will discuss some basic information about I2C. I2C stands for Integrated Circuit and is a synchronous serial communication interface, much like SPI. I2C was designed by Philips in the early 80s and was intended to be used for the communication of multiple integrated circuits on the same PCB. But it's not limited to inter-PCB communication and is nowadays more or less a standard for the communication with sensor ICs that might even be connected over fairly long wires. The original bus specification reaches speeds of up to 100 kilobits per second, with a fast mode of 400 kilobits per second added later. And also a super fast mode was added in 1998, which can reach up to 3.4 megabits per second. While these speeds indicate the maximum clock frequency, there's actually no minimum speed limit. Different variations of the bus also exist, like for example the SM bus. One of its major advantages over, for example, SPI is that it requires fewer wires. Just 2 wires are used, one for the clock, remember it's a synchronous protocol, and one for the data. These lines are called SCL, which stands for Serial Clock Line, and SDA, which stands for Serial Data Line. The communication follows the master and slave methodology, with a dedicated master that schedules all communication. The most minimalistic I2C setup you can imagine has just one master and one slave. However, you can have multiple slaves and also multiple masters as well. Each slave has a dedicated 128-bit address. If a master wants to read or write a certain value of a slave, it needs to indicate it by sending this address over the bus together with the read or write request. Each slave listens, and only the slave with a particular address is supposed to answer. As you can see here, 2 pull-up resistors on the SDA and SCL lines are also required. That's because all I2C devices connect to these lines via open drain output drivers. So in order to ride a line low, the transistor needs to be switched to connective state. In order to ride a line high, the transistor needs to be switched to blocking state, and the line is held high via these external pull-up resistors. To dimension these resistors, we need to know the specification of the I2C circuit, meaning the maximum speed and the wire capacitance. There are multiple guides to calculate the perfect resistor value which maximizes speed and trades off power consumption. I've linked them down in the video description below. But I would actually argue that for 99% of all cases, you only need this formula here. Tau equals R times C. If you measure your wire capacitance, you know C. And if you look for the maximum T rise of your I2C speed, you can calculate R as R equals tau divided by C. For the example of around 200 picofarad and standard mode, which allows for a maximum T rise of 1000 nanoseconds, we get 5 kiloohms. In this video, we will take a closer look at the following setup. An ATmega328P connected to one inertial measurement unit. In particular, we use an MPU9250. The ATmega, which is the microcontroller on this Arduino Uno board here, is connected to a computer, which also powers the complete setup via USB. The IMU is powered by the 5-volt supply of the Arduino, internally just wired to the USB power supply. And we then of course connect all modules to a common ground. The I2C lines, SDA and SCL, are directly connected to the IMU. You may then stumble across these 2 resistors here. These are the pull-up resistors we talked earlier. I selected 4.7 kiloohms here. So if something is wrong or just not actually as you expected, first take a closer look at your setup and see if you haven't forgotten these pull-ups here. To see how the bus system is actually working in detail, I've put some demo code on this microcontroller, which simply reads out the Who Am I register of this slave each 100 milliseconds. Using the Arduino framework, this is actually fairly simple. Start a transaction with the slave at the particular 128-bit address, send the register to read, and request 1 byte from the slave. The remaining code is just for printing and waiting. So let's hook up our oscilloscope to the bus and see what's going on there. For many high-end oscilloscopes, you can set specific triggers for different communication protocols and even for certain states or addresses sent over the bus. We could, for example, set a trigger to the start condition of I2C. However, this fairly old oscilloscope here does not support that. Still, we can set the trigger to be a falling edge of the SDA line to start seeing something. Perfect! Now we have a single shot of the full transmission. I sketched this transmission for you on the slide so we can take a closer look at it. The transmission starts with the start condition, which is a specific symbol that can only be sent by the bus master, here the Arduino microcontroller. As I've already told you, the master schedules all transmissions over the bus. There is no way that a slave by itself can start sending data over the bus. Never. Okay, so it starts with the start symbol, which is the SDA line going low while the SDA line is still high. Afterwards, the master drives the SCL line according to the chosen I2C frequency. In this case, this is 100 kHz, which we can tell by just looking at the time resolution here. The data bits are sent over the SDA line. The symbol 0 corresponds to a data bit of 0, and the symbol 1 corresponds to the data bit of 1 is a high SDA line. The SDA line symbol is only valid and should only be interpreted by the slave when the SCL line is high. When SCL is low, it might still change. In this case, the master is sending the particular slave address he wants to communicate with. This address is 7-bit width. The 8th bit is the so-called read-write bit. If this bit is set, so SDA is high, the master wants to read. If this is not set, so SDL is low, he wants to write to the slave. In this case, the read and write bit is not set, which means the master wants to write. You may now wonder, as we wanted to simply read the Who Am I register from the slave, right? But actually, we somehow need to tell the slave which register address from it we want to read. To better understand this, we can take a look at the datasheet of this particular IMU and search for the term single byte read. Here we can actually see how it's supposed to work. We have to send the start condition, then the address of the slave, and as indicated here, also the write bit. This should then be acknowledged by the slave. After that, the master sends the register address he wants to read. In our case, that's the Who Am I register. This is then again acknowledged by the slave. After that, we have a so-called repeated start condition, after which the master again has to send the address of the IMU, but this time with the write bit set to read mode. This is then again acknowledged by the slave, and finally the slave sends the data inside the particular register. This data now is acknowledged by the master, in this case with a neg, so not acknowledged. The transmission is finally terminated by the so-called stop condition. Let's take a look at this in our demo setup. We have the start condition, the IMU address followed by the write request, all sent by the master. The slave then takes over the SDA line and sends the acknowledgement bit. We can see this if we just disconnect the power of the IMU. We can now see that the request is now not acknowledged by the IMU, which previously pulled this line low here. Okay, now let's reconnect the IMU. After the IMU here acknowledged this write request, the master sends the address of the register he wants to read. The Who Am I registers according to the datasheet at address 0x75. And here the slave acknowledged again. After that, you see the master is now sending a repeated start condition with SDA going low while SCL is high. Remember, that's not allowed during data sending. This repeated start is followed by the register address of the slave again, with the read and write bit set to read. After that, the slave again takes over the SDA line, acknowledges it, and sends the data. Here 0x71 in hexadecimal. Let's take a look at the datasheet if this is actually expected or not. Therefore, we take a look at the default value for the whom_I register, and indeed it says 0x71 to be the expected value here. Perfect, we have successfully decoded the transmission. So let's summarize. In order to read 1 byte of data, the master needs to send the slave address with write request, send the register address he wants to read in the following, send the slave address again with a read request. After which a single byte can finally be read. That's sending 3 bytes or even 29 different symbols before 1 byte of data can be read. Sounds quite cumbersome, right? As you've seen by the datasheet, the IMU also allows for that what's so-called burst read or write of data. This is quite common for I2C enabled devices and allows one to keep reading registers one after the other without having to send these 29 symbols before each byte. But what is actually sent by the slave after the specific register address that we asked for? It keeps incrementing this address and sends the data of the next register. This is also why commonly used registers, such as different sensor values or configuration parameters, use adjacent register addresses. For example, this particular IMU here stores its acceleration and gyroscope readings all the way from register address 0x3b to 0x48, so that they can be read in burst mode. To read out these values, we will add some small lines of Arduino code to our test setup. A little bit of coding and you are even able to control your computer's mouse using this IMU. Okay, now let's recap. I2C is a synchronous serial bus system designed to connect a processing unit, such as a microcontroller, to one or multiple other systems, such as sensors. It uses a master and slave methodology with typically one master and multiple slaves. However, a multi-master mode is also possible, but that's just beyond the scope of this tutorial. The master initiates all communication and is then addressing a certain slave by its specific 128-bit address. This means all slaves need to have different addresses. It allows for some decent bus speeds too, from 100 kilobits up to 3.4 megabits, and can be used to connect systems even over longer physical distances. That's it for this short I2C tutorial. If you have further questions, write them down in the comment section below. If you like this tutorial, give it a brief thumbs up, and if you don't want to miss out on upcoming ones, subscribe to the channel and ring the bell.